Hi, everyone. Thanks for having me. So this isn't about consciousness per se, but I hope to give you a high-level overview of the work that I've been doing with Bob Cook here in Oxford. And hopefully in the discussion, we can try to relate it to something about consciousness. Now, the starting point of this project was a thought that I had about the Penrose staircase and the nature of it. It's a very mysterious thing that you can picture in your head, but it doesn't quite have a physical model because we can envision in our head the little figures walking up and walking down, despite not having a physical model. And for someone interested in modeling space, this presents quite a challenge because how do we make sense of these kinds of impossible spaces in our head? And that was the kind of motivation going into this. And Bob Cook recently gave a talk on the same thing, but more from the quantum computing angle recently at QISS, and that talk should be online soon. So there's a different angle to the one I'm presenting here. And so the question we were trying to address is, what is a suitable model of space? And by suitable, I mean the kinds of space that we might entertain in our heads. And one thought was, well, how about language as a model of space? And what do I mean by that? Well, language is pretty good at describing space. One function of language is coordination in space. So, hunters will talk to each other about where the prey is in space. And language itself is very deeply intertwined with space. There's a lot of spatial content in language. So language and space already have this familial relationship going. And so our question was, can we use these linguistic descriptions to probe space? After all, it is fair to describe the Penrose staircase as a staircase that forever ascends upwards. So here's the plan for, oh, no, not yet. So we're going to start the investigation by taking a compositional theory of language meaning. And we're going to try to make the spatial meanings explicit in this model. And as a result, we hope to obtain some inferences that require awareness of space. For example, the one that you see here, if the light is above the painting and the painting is above the chest, then we'd like to kind of get at, oh, well, the light is above the chest. And so the plan of this talk, very briefly, is I'm going to give a high-level overview of the graphical calculus of sets and relations, in particular touching on spiders, or Frobenius algebras, quantum algebras, as they're also known. And then I'll go over what Discocat and Circa are briefly, and hopefully we'll get to some examples. So the graphical calculus, which I suppose you'll be seeing a lot of in this session, well, we represent individual relations as boxes, and more general boxes can have multiple inputs and outputs to relate different sets to each other. And we notate two special cases, which reading top to bottom we call states and tests, special kinds of relations that are just subsets. And since this is a mathematically inclined audience, I'll skip over the details of sequential composition, but here's the graphic. We'll share the slides at some point. And what's important to note is that graphically, sequential composition is just depicted as plugging in boxes one after the other, reading top to bottom. And parallel composition, or holding two relations at once, we depict as sticking two relations side to side, as two boxes side to side. And once we have this language of sequential and parallel composition, we can create some quite nice looking diagrams that describe a logic of how to compose relations. And what's special about relations and some other settings, such as that of Hilbert spaces, is that there are spiders that are special relations, which essentially enforce that for some number of input sets and some number of output sets, all the same set, that all the inputs and all the outputs must have the same value. And the key property of spiders graphically is that if two spiders are connected, then they fuse. So spiders are a family of relations over copies of sets. And we have two special cases of spiders. One can be read as a copy operation. One can be read as a delete. And the upside down versions of those do something quite like AND. So if we have two subsets Q and R, the spider that takes the AND returns their intersection. And if we have the spider that only gives an output, then that's giving out the entire set, which we treat as unknown, saying, well, we don't know which of the things we're talking about in the set, so we'll give you all of it. And here are some of the graphical properties of spiders. The spider with just one input wire and one output wire is the identity relation. There are two very special spiders called the cup test and the cap state, which satisfy this yanking equation. And what you can do with these cups and caps is you can freely turn relations into subsets and vice versa, subsets back into relations. And so that was a speed run of the graphical calculus of spiders. And now to talk about this Discocat briefly. So there are lots of algebraic approaches to grammar where individual words are assigned types in some algebraic system. And the idea of an algebraic approach to grammar is to take this list of algebraic types and try to find some kind of algebraic reduction to a special type, say S for sentence. And the idea of Discocat is, well, we can actually depict these algebraic reductions as string diagrams. So what this is depicting here is that Alice is a noun and Bob is a noun, and this transitive verb chases is something that's waiting for a noun on the left and a noun on the right. And once those guys are plugged in, you're left with a sentence type. And so the entire sentence is grammatically correct. And what's interesting is that if we go to somewhere like Rel, we can plug in these boxes on top of the string diagram that represents the algebraic reduction to that proves a syntactic correctness. And now we have a relational model of what it means for Alice chases Bob. If we supply just the meanings of Alice, chases, and Bob, then the algebraic reduction gives us the instructions on how to plug together meanings so that the output is a state that describes the meaning of the entire sentence. So in this sense, we have a compositional model of meaning where the composition follows the structure of language. And recently, we've upgraded this formalism to get to disco-circ. One thing that you note here for sentences is that, well, we always get out a single wire, a sentence type. But if we are to consider something like text, then we would like perhaps some more structure so that we can compose different sentences together in a text. And we do this by introducing internal wirings, a full formal account of which is forthcoming with Bob. But the idea is that, well, if you introduce some internal wirings using spiders to word boxes, then we can topologically manipulate these spiders, and that's the nice thing about them, to get out what looks a lot better in terms of ability to compose. We have here a sort of fragment of a circuit. And what we can then do is say, well, then we can model entire texts by taking the sentence for the painting is above the chest and the sentence for the light is above the painting. And now we can compose those sentences as we would compose gates in a circuit to obtain a large circuit that, all in all, produces an entangled state that describes the relationship between where the light is, where the painting is, and where the chest is. So the structure of the text becomes the structure of a circuit. And if we were to plug in a specific model of meaning, so now if we were to interpret all of this, say, let's take the space to be R3 and we interpret above in a sort of minimalist, sensible way, then we can compute as we compute in Rel. And if we delete the position of the painting, say, okay, well, I don't care where the painting is, I just care about where the light and the chest is, we can push through a computation and we can conclude that, oh, very well, the light is above the chest, which is what we wanted. And just as a side note, it is possible to do this completely graphically as well, because recall that we had an AND operation. And if we can demonstrate an equality that P and Q is the same as P, then we have a synthetic graphical definition of what it means for P to entail Q. And so if we were, not that we have to, but if we were to axiomatize some of our spatial relations, then we could say, well, okay, let's say that states are idempotent with respect to the spider, which is that if I have where something is and I intersect that with where that something is, that's the same as where that something is. And the second equation here is depicting the transitivity of above, then I can push through a synthetic derivation of the same fact. So from what we had before, I'd like to entail that the light is above the chest. And what I can do is I can do a little spider manipulation, all of it's topological, apply the first idempotence equation, apply the second one, and I get back the first premise, and I've synthetically concluded that, yes, the entailment that I want holds.
I mean,
so where this starts becoming interesting is when we start using language to point at things. So for instance, if we had some model of the chessboard, let's say, and we know what pawns are, so we can indicate the algebraic coordinates on the chessboard of where pawns are and where kings are and where knights are. Suppose that we have this problem where I'd like to, without resorting to the algebraic coordinates, point out the location of a pawn. And this is sensible because two people might be looking at the chessboard from different positions. They might not be aware of what coordinates there are, and it's not like real life carries coordinates with it. Yet we are able to use language to point out spatial locations. So one thing that I could do to describe the location of this pawn is say, well, it's the pawn next to a king that a knight can capture. And plugging in our models of meaning, we can compute these. So piecewise, if I just compute, okay, I want to find a pawn next to a king. So I deform a bit and I push through a computation and I isolate some locations that, the point is I want to isolate some locations that this pawn could be. So I know how to compute next to and a king. And that gives me a list of squares that are next to a king and I know which ones are pawns. So intersecting those two, I get out all those pawns that are next to kings. But this isn't quite enough to specify the pawn on g6 that we want to point at. So we further specify that, well, it's the one that a knight can capture. And we do a similar kind of computation, and we find that, okay, well, this uniquely specifies the pawn that we want. And the nice bit about this is that you can have two parties that have very different internal representations of what is going on the chessboard. But as long as they agree at the level of language, as long as they agree on the names of the pieces and the rules of chess, the linguistic description enough can coordinate a spatial location in the public domain outside of what is privately inside their heads. And so we return to the Penrose staircase and we find that, yes, we can describe a toy model of the Penrose staircase where we identify the four corners with, say, 1, 2, 3, and 4, and we can describe, well, okay, well, 2 is above 1, and 3 is above 2, and 4 is above 3, and 1 is above 4. And the hope is that, well, maybe this is enough. If we were to interpret what we meant by this in R3, we're able to show that, well, the Penrose staircase is impossible in R3. There's no such satisfying entanglement of those 4 points in R3 modulo a sensible definition of above where a Penrose staircase can make sense. But then what does it mean to have a sensible notion of where it would make sense? Well, we claim that in some cases this circuit is good enough as a representation of what we mean by this space. And so what's the upshot of representing everything with these circuits? Well, the practical upshot is that circuits are nice to compute with. When we are able to separate the concerns of grammar and the meaning of individual words, then the hope is that we achieve some sort of computational efficiency. And this is the subject of ongoing experiments here at CQC, at the Compositional Intelligence branch here in Oxford. So they're quite nice because these circuits are also interpretable in the setting of machine learning, and the hope is that we're able to do something interesting there. The theoretical upshot is that this provides us with a different way to structure space. And what do I mean by that? Well, we can formalize what we mean by Cartesian space or a Euclidean space without directions, say, by using Cartesian space, using 3 coordinates to point out locations. We have other notions of what space means, for example, a topological model of what a space might be. And here we're suggesting that, well, we have another model, which is just the list of descriptions of what is in that space and what constitutes that space. So in a sense, we're using the structure of language to now provide a separate formal model of what it would mean, what the structure of a space is. And these circuits stand independently as abstract objects before one wants to interpret them in Cartesian space or in a topological setting or what have you. There's an empirical upshot as well. So Gardenfor's claim is that geometry is a mediator between the raw sensory data. Thank you. That geometry is a mediator between the raw sensory data that we receive and the eventual symbolic descriptions of the world that we have. And the upshot of this is that, well, he's claiming that concepts are structured geometrically, for example, the color cube or a space of tastes. And having this now formal link between the structure of space and the structure of language, we can see if, in computational experiments, whether there are efficiencies to be gained if we pretend as if the machine that is learning is embodied in space and has the ability to organize their senses in a similar way that we do, spatially. And finally, I suppose, an aesthetic upshot is that the diagrams are quite nice to work with and very intuitive in my mind. And that's it. That's all. I think I've gone through this fairly quickly. So thank you very much for your time, and I'd love to enter discussion now.